Okay, in this lecture we're going to discuss the efficiency of algorithms, and I'll probably break this up into a couple of different lectures. And so for algorithms, the attributes we're interested in are the correctness of the algorithm, first of all. The algorithm should produce a correct solution. And we're also interested in the ease of understanding as far as the pseudocode, so that if you were to describe your algorithm to someone else, and give it to someone in pseudocode, they should be able to understand it and reproduce it. And the elegance just relates to how simple it is, how simple the solution you came up with is. So it should be sort of parsimonious. And then efficiency relates to the time and the space. So we're going to get into that more, but with time, we're really more concerned with a unit of work versus time in terms of minutes or seconds. And space relates not just to actual memory or RAM, but it's actually more of a relative type of way to measure the amount of memory that the algorithm is going to use. And so what do we mean by the algorithm's time efficiency? Well, it should be something that relates to a general unit of work. Now, we don't want to use minutes or seconds, because if you're running a program on let's say a Mac versus running it on like a Solaris computer, which are computers which have different architectures. So you can't expect that they would run exactly the same, because the underlying computer instructions, when they take your algorithm, are going to be a little bit different. So we don't want to rely on time in terms of seconds or minutes or anything like that. We want to find a sort of general way to, or an independent way to express the time it would take for the algorithm in terms of the input size of what you are trying to compute. And so the choice of the algorithm is also important. You need to understand what the algorithm is doing, because you could have two different algorithms that are trying to solve the same task. You could have, for example, two algorithms that are trying to search for a name in a list, like in a directory, and one algorithm could do very well when the list is already sorted, but the other algorithm could do much better if the list is, let's say, random. So you have to understand what the algorithm is doing in order to pick the best one. So as I mentioned, common tasks for algorithms in terms of what we're going to be studying in this unit are searching and sorting. And so there's two different ways that we're going to explore searching of data, and one is a sequential search, and the other one is a binary search. And for the sequential search, we're going to go through an algorithm that shows how to find some value in a list in a sequential order. And the binary search is going to be a little different. It's going to be a lot faster way to find the data you're looking for. So as I mentioned, the sequential search, we're going to search for a name among a list of names. So let's say we have 10 names that we have a list of, then that means n would be 10. So, and let's just pretend this is going to be a directory that we're going to look at, as I said. So we're going to start at the beginning, and then we're going to compare the name that you're looking for to each entry in the list until you find a match. And here's an algorithm of how you might do such a thing. And so we can walk through it step by step. So the first step says get the values for name, and that would be basically the name that you're going to look for, right? And then n is the size of your sample set that you're trying to search on, and then the big N's are all the basically all the names in the directory, and the T's are the telephone numbers. So the step 2 says set the value of I to 1 and set the value of found to no. So in this step we have two variables. There's I and found, and I is just going to keep track of where we are in the list, and found is going to keep track of whether or not we've actually found that name we're looking for. Step 3 says while found equals no and I is less than equal to n, do steps 4 through 7. So this is our loop construct, and it has a condition of checking to see if we found the name, and also to check to see if I is less than or equal to n. And the reason why we have those two are if we found the name, then the while statement, once it goes back up to step 3, will know that we can exit out of the loop. But let's say we would never find the name, so in order to determine that that we haven't found the name, we basically would have to know that we've been through all the values in the list. So if we keep track of I and increment it each time we check for the name in the list, if it's greater than n, then we know we haven't found the name in the list. So step 4 says if the name is equal to the ith name in the list, then you print the name of that person and set the value found to yes. So that means you found it, and basically you're just printing the information, and then it's not going to go to the else statement, which would be step 7. So it's going to skip over that because the if condition has been satisfied, and then it would next go to back to step 3, and then found would be equal to yes. So the while loop would terminate, and then it would go to step 8. And in that case, since found is yes, it would not print that sorry message. But let's say that it did not. There's an example that we did not find the name. So what it would do each time, we're starting back at step 3, let's see, it would go through step 4 and do that check. It would not go to 5 or 6, and then it would go to the else statement and say add 1 to the value of I, then go back to step 3, and then it would do the check, and it would say, well, I is less than or equal to n, so keep on going, and we haven't found it yet. And then it would go to step 4, do the check, and since that wouldn't be satisfied, it would go to the else statement, and then add 1 to the value of I, and then keep on repeating over and over again until the value of I is greater than n, at which point it would exit out of the loop. And then we'd go to step 8, and it would say if found equals no, which that would be the case because we haven't found the name. It would print out the message, and then it would stop. So there you have it. That was the sequential search algorithm, and the central task, if you want to think about what is the main thing that we're doing in this while loop or in this algorithm, is to do a comparison to check to see that if we have found the name. So that is really what your measurement or unit of work is the comparison step. The other tasks, as far as incrementing the value and outputting the results, they're just basically peripheral tasks, and they don't contribute to the amount of work. They're not good measurements in terms of how to really quantify how much work you're doing. So the central task of the sequential search, as I said, is the comparison step, and we're doing one comparison at each pass through the loop. So in order to get an idea of the efficiency of the algorithm, you have to know how much work is the algorithm doing. So in this case, we want to figure out how many times is the loop going to be executed. So in order to determine this, you kind of have to know when and where, or where and if we find the name in the list. And in the best case is that the first name in the list is the one that you're looking for. In the worst case, if the name is found at the very end of the list, or if the name is not in the list at all. And in the average case, it's if the name is found somewhere in the middle of the list. So that would make, let's see, so if we want to talk about number of comparisons, the formal way of doing this with algorithmic analysis and complexity is to discuss these different terms here. There's best case, which is big omega, and worst case, which is big O, and average case, which is big theta. In computer science, we generally like to use the worst case scenario because we're always interested in finding out, what is the maximum or the most time an algorithm is going to take, because you need to always prepare for the worst case scenario. So in this case, the worst case scenario would be order big O n, and the n is because if you have, let's say, 10 elements in your list, then n would be 10, and if the last element in the list was the one that you were looking for, then it would take 10 comparisons, which is equal to n. So we're really not interested in the behavior when n is a small list, but we're actually more interested when it gets very large. And that's why, when there's only 10 items in the list, whether or not it's the first entry in the list or the last one is really not going to make a difference. But let's say there were 1,000,000 items in the list, then whether or not it's the first one or last one makes a huge amount of difference.